So let's begin then with the simplest of our states. So let's test the time-independent Schrodinger equation on our ground state. Let's begin with that. So let's begin with the simplest case. And then as we move our way up to the more complex cases, we can step by step build up the lessons we need to know how to use these new types of operators. So let's begin with the Hamiltonian applied to our ground state. Well, we now have a nice expression for the Hamiltonian. So we can rewrite this as a hat dagger a hat plus a half, acting then on my ground state. Very good. Now, we notice a few things. The first is that I have to apply a hat dagger to the result of a hat applying to the ground state. Plus, then we get back 1/2 of the ground state. Now, this last term, the 1/2 of the ground state, well, that's something we recognize and something we're very happy with because that really is just a constant times my ground state. This looks perfect for some kind of purity test on the Hamiltonian. So I like this term. This term over here at first looks a little bit complicated, but remember, this is the result of applying a hat dagger on the result of a hat being applied to phi naught, and we know something very special about the ground state. You will recall that's one of the key identities we had mentioned, proved at the end of last lecture, and is right up here in our summary. Whenever a hat applies to phi naught, we end up with exactly 0. So this term will give me 0, and I get back exactly, when I apply my Hamiltonian onto my ground state, nothing other than just a constant times my ground state. And I can read off then the ground state energy very nicely from that constant. That energy must equal 1/2. So all of this works out here very nicely. Okay, that was the ground state. Let's try the first excited state. In our way through this one, the algebra is going to get a little bit complicated at first, but then we're going to learn a very important final component for the algebra among these a hat operators that is going to allow us to actually understand the future states as well. So let's take a look at that. So now let's test our Hamiltonian acting on our proposed, right, first excited state, and we're hoping we will get back then just some energy times that state, but that's really something we're testing now. So I'm not going to be assuming this. That's just sort of our inspiration. Now when I apply the Hamiltonian on phi 1, the Hamiltonian itself is again a hat dagger a hat plus 1/2, and that then is now to be applied to our anticipated first excited state. This is a state that we realized we could create with the a dagger operator acting on the ground state. So I know this is its own Fourier transform. I also know it has one node, so this is a very good candidate for that first excited state. The real question is whether it actually does satisfy the time-independent Schrodinger equation. So let's move along following the same sort of pattern as before. You'll notice I have then a hat dagger a hat now is acting on the result of a hat dagger applied to phi naught. So this is a bit of a more complicated expression. And I also have coming back out at me, again, 1/2 times the state I started with. So that will be 1/2. And this here part, again, I recognize this is my phi 1 state. Right? That's how we had constructed it. That's what we were applying things to. So I get back 1/2 phi 1. So again, the second piece I'm happy with because this is just a constant times the state I started with. That's looking very good. This piece, though, is looking a little bit more complicated. In the last case, we were very happy because we had a hat applied to the ground state, and I could just then eliminate the term completely. In this case, we don't quite have that. I sort of very much wish I could commute a hat and a hat dagger. They may or may not commute, however, so I have to be careful how I do this. But I want you to notice a very powerful little trick that we often can use when we're dealing with operator algebras. So this key trick is to notice the following. I really wish I could commute these. I don't know if I can. So I'm going to rewrite this term as a sum of two different terms. And watch carefully how I do this. First, I'm going to put the commutator bracket around these two. The commutator itself will give me a plus sign with these in their original order. So the first term in this commutator won't have changed the value of my expression at all. There will be now, though, an additional term, which will be minus what I get when I flip the order of these two operators. So I'm going to also get what I've written down also has a minus term, which looks like a hat dagger, a hat dagger, a hat, right? Because I've simply written these now in their reverse order, acting on phi naught. Now notice, the commutator gives me this term with a minus sign that wasn't there before. So to ensure that I've done nothing to the value of this expression, I should add this term back again, right? So as soon as I've added this term to the above term, I'm back exactly where I had started. In terms of it being equal. The advantage of doing this, though, is that now I've got the a in the location I want. I've managed to actually commute the two, but the cost of doing that commutation is the additional term that you see up here. So if I wanted to write down the trick sort of in a general algebraic way, what I'm really saying is that if I ever have an expression like a hat, b hat, c hat, d hat, right? And I wanted to rewrite it with two of my operators in the opposite order, the way I can do that is to put a commutator bracket on these two, right? Which gives me the first term exactly as I originally had it, and then add to this the term where the two operators are now in their commuted positions, because the commutator also comes in with this minus term, and I'm just adding it back in. So that's a very general trick you can do, and we want to keep that in mind for the future. So we now have ourselves with a nice equality, this whole thing, so I'm going to actually put some parentheses around it so we recognize that it's all of these terms now that I need. The sum of all these terms is the result of my Hamiltonian on phi 1. And it's looking pretty good, right? Because this a hat on phi naught, we know, as we had seen before, will give me 0. This term is just a constant times my original state. So this all looks very nice. The big question is, what is the value of this commutator? Once we know that, we will be able to come back to this expression and know whether we have satisfied our time-dependent Schrödinger equation. So let's continue on then with our analysis. So the next question is, okay, what is this commutator? A with a dagger. Now, we can begin our analysis by recognizing what A actually is. The A operator, you will recall, is x plus d by dx, right? And that's being commutated with a hat dagger. Now the commutator has a very nice additional property that we can use if you think about it, right? What I'm going to write down for this is, x plus d by dx applied to a hat dagger, and then I'm going to subtract it with this applied on the other side. So there are two types of terms. There's the type of term which has just the x, and that x will appear on both the left and the right of the a hat dagger. And then added to that, I'm going to have the d by dx, which also will apply on the left and the right of the a hat dagger. So this will take on then the value of x commutated with a hat dagger plus d by dx commutated with a hat dagger. If you want to think about this, there's another trick involved, right? All I'm saying is that if I ever have a plus b commuted with c, well, that is just a commuted with c plus b commuted with c. Very common sense type of result. And we can do this operation yet again on the other side, right? A hat dagger is x minus d by dx, And for the other bracket, right, a hat dagger again is x minus d by dx. And once again, I can use this linear property of the commutator. It works just as well on the other side. I could have A commute with B plus C, which would then be A commute with B plus B commute with C. I'm sorry, A commute with C. I miswrote that there. Plus A commute with C. And this works for exactly the same reasons that the other trick worked. Very good. And in fact, if you reverse the orders here in these commutators, we already know all that that does is flip the signs. And if you reverse the orders here, you would actually be proving this identity. And in fact, I think I'm just going to rewrite it corresponding to that. It's kind of a more fun way to write it. So I could have looked at C commute with A plus B, and sure enough, that would be C commute with A plus C commute with B, which I can get just by switching the orders here and putting in all the minus signs. Okay, so those are two more tricks that we can use for any commutators. Working away here on the commutator that I'm trying to compute, this will give me then x commute with x, minus sign can come out, right? X commute with d by dx, plus d by dx commute with x. And then finally, I'm running out of space on my line. I've got d by dx commute with d by dx. Very good. Now, as I'm writing this out, you should be able to notice the values of each of these different individual commutators, right? So x commute with x, well, that's just a 0. d by dx commute with d by dx is 0. d by dx commute with x is something we've already done. That was just the identity. And this is just that same commutator, but written in the backwards order, so I know the result of this commutator itself is a minus 1. So the final result that I see here is going to be minus 1 plus 1 is 2. Now, this looks great. You can see, though, if you've been paying attention, I've made one little mistake, right? The definition of a hat dagger is not x plus d by dx. That has to be divided by the square root of 2. So I have an extra factor of square root of 2 in here. And then when I substituted in for a dagger, there was another factor of 1 over square root of 2 that I should have had in my definition. So this is divided by the first square root of 2 was coming from the first line, and then there was another square root of 2 coming from the definition of the a hat dagger operator. So there's 2 root 2's in that denominator. And likewise over here, there's the original root 2, and then the root 2 that comes from this portion in the commutator. And each of these two terms then has 2 1 over root 2's, so there's an overall factor of 1/2. So I'm kind of glad, actually, I had made that mistake. Hopefully you guys had caught it. But you can see then that's an important factor to keep in mind, because once I've put in this additional factor of 1/2, what I really had was a 1/2 out in front, and inside the brackets, once again, I had gotten a 2. The bottom line is this commutator is something very simple. It is just the identity. And that is the last and very key piece of algebra that we can then use to prove all kinds of great identities and results using these commutators. So let me put a box around that. So that answers that key question for me in terms of what that commutator was. And this now takes me all the way back then to our original calculation, which was where we were applying the Hamiltonian to phi 1. And what we learned from this thing is that, in fact, this commutator is just the identity, I, and now 1, I mean, and now we have a very interesting result, because this just gives me a dagger phi naught, which is just phi 1 plus 1/2 of phi 1. So this gives me a hat dagger phi naught plus 1/2 of phi 1, which equals then phi 1 is what the A dagger does to my phi naught. That's what we had started with that state, plus a half of phi 1. So the result is 3/2 of phi 1. And that is a beautiful and key result, because that tells me that phi 1 is indeed a pure state of my Hamiltonian. So let me just write that down here a little bit more clearly. I'm sorry, I think we got a little jammed up here on the screen. That's 3/2 phi 1. That's a very happy result, because then that proves that, in fact, this is a pure state. It had one node, so we know it has to be the first excited state, and I can pull off the first excited state energy directly from this relationship, and that's just 3/2. And this is all a super happy result. It's our first new proof of an eigenstate. So let me put my happy professor symbol on there, and I'm going to put a box around this key result. So phi 1 is, yes indeed, as we had conjectured, the next excited state with exactly the 3/2 energy that we had expected. Beautiful. So the next thing then I think we want to consider is what happens if we go up in energy yet again.